Good afternoon, students. In the previous lecture, we studied about phasor representation, how we go from time domain to phasor domain. Phasor representation means frequency domain representation for signals, for voltages, for currents, and also circuit elements. If we see here, for example, Vs of t, this is time domain 20 cosine of 40 minus 15 degree. This will be represented in phasor form. We remove the time domain, it will be 20 e to the power of j minus 15 degree, or 20 at an angle of minus 15 degree. So we try to solve this equation to find this problem, to find the output voltage. We formulated the KCL at node A, and we found the integral differential equation, and we derived this differential equation. So the target is to find the output voltage for this circuit. So we said this technique, it can be tedious, for example, for more complex circuits, and we are talking how this can be simplified. So instead of first deriving the differential equation and transforming it into phasor to solve the output voltage V naught, we can transform all the RLC components into phasor first, and then apply the laws, the KCL laws, KVL laws, and other theorems. So that's the target of this lecture. So what is a phasor representation for circuit elements? If I have a resistor, simply the voltage in time domain is I small r times resistance, and in phasor form V equals to the phasor current I times the resistance. And if I have an inductor, the inductor current I and the voltage represented are related by VL di by dt. So in phasor form, it will be di by dt means derivative. So in time domain, derivative is it will be j omega in frequency domain. So j omega L times I. So j omega times L means the impedance of the inductor. It's like resistance. The inductor has its own impedance, and we say the impedance of the inductor is j omega times L. And I, the current through the capacitor, is C dV by dt. And that means the phasor current I, again, dV by dt is j omega. I is equal to j omega times C times V. So if I have here, you see the voltage V here, and as a function of the current, this is if I see the voltage and the current relationship here, for the resistor case, they are in phase. The current and the voltage are in phase. What about for the inductor case? The inductor, I have J, V is equal to J omega L times I. So that means there is a 90-degree phase shift. A 90-degree phase shift. So I have the current I here. So the voltage is J omega L times I. So it is 90-degree ahead of the current because of the J part. So it will be the voltage will be leading the current. What about for the capacitor? The capacitor is I is equal to j omega CV. So the I will be leading the voltage. So I is here, the phasor I, and the voltage V. So they are 90-degree. There is 90-degree difference, but the current is leading the voltage. So in an inductor, the voltage is leading the current. In a capacitor, the current is leading the voltage. So this is summary. In time domain, V equals to Ri for the resistor. For the inductor, VL di by dt. For the capacitor, I C dV by dt. In frequency domain, for the inductor, for the resistor R times I. These are phasor forms. V is in phasor form, I is in phasor form, and the voltage for the inductor J omega L times I. Okay, so the phasor current I times J omega L, that means, and the voltage across the capacitor I over J omega C. Example, if the voltage is 6 cosine 100 t minus 30 degree is applied across a 50 microfarad capacitor, calculates the current I of t, I as a function of time. So what we should do, we first find the voltage in phasor form and we change it to time form. So first the source voltage 6 cosine 100 t at an angle of 30 degree, which means V is equal to 6 at an angle of minus 30 degree. So it's at an angle of minus 30 degree I have here. What is omega? Omega is 100 because general form, remember the general form is cos omega t plus phi, the phase. So omega is 100, capacitance is 50 microfarad. So what is the current? I is j omega c times V. This is a relation between the current and the voltage across the capacitor. That means what is V? V is 6 at an angle of minus 30 degree times omega c plus 90 degree. Why? Because the J part, for the J part we need to add the phase 90 degree, and then now it's a matter of substitution of the numbers. 6 times 100 times 50 10 the power of minus 6. So the current finally is 30 at an angle of 60 degree. But what is this? This is phasor form. So I need to change this to time domain. So to change it to time domain, we just say I of t is the real of the phasor current times e to the power of j 100t, where 100 is omega. All right. So this will be real of 30. The polar form of the current is 30 at an angle of 60 degree. 30 times e raised to j 60 degree times e raised to j 100 t. Then it will be 30 cosine of 100 t plus 60 degree milliamp. So we need to take care, of course, the units. All right, now the impedance and admittance. The impedance of a circuit is a ratio of the phasor voltage over the phasor current. So V over I. In general, impedance will be a complex number, R plus JXC, or it is in phasor form Z at an angle of theta. The magnitude of Z is R plus square root of R square plus X square. The phase is tan inverse of X over R. If we have a purely inductor element, then it will be Jx. There is no R. So X will be omega L, for example. If it is a capacitor, it will be minus J omega C. So X will be minus omega C. So R here is the real of Z and X is the imaginary of Z. The reciprocal of impedance is admittance. Y is equal to 1 over Z. And the unit is Siemens or mho, MHOS. So it is current over voltage. In general, the admittance will have real part plus imaginary part. And after some calculation, we'll find G is R over R square plus X square, and B is X over R square plus X square, where G is the real of Y and is called the conductance, and B is the imaginary of Y and it is called the susceptance. All right, so here again, impedance and admittance of passive elements. R for the resistor Z equals to R. So I will have the real part and the admittance Y over 1 over R. Remember, this is called conductance, 1 over resistance. L, Z equals to j omega L, Y 1 over j omega L, the admittance. C, Z is equal to 1 over j omega C, and Y equals to j omega C, the admittance for capacitor. Now let's see what happens to the inductor and the capacitor for DC and for high frequency. For DC, as you know, this Z is j omega L for inductor. For DC means frequency is 0, omega is 0, so Z is equal to 0. So the impedance is 0, means it is short circuit. Remember when we studied in chapter 7 and chapter 8, we said an inductor is short circuit for DC. That's why here also when omega is 0, Z is equal to 0. When omega is increasing, or when the frequency is increasing, and in the limit when it goes to infinity, Z is equal to infinity. It will become open circuit. And what about for the capacitor? The capacitor, what is Z? Z is 1 over j omega C. And for DC, when the frequency is 0, 1 over 0, infinity. So the capacitor will become open circuit. What about for high frequencies? For example, in the limit, when the frequency is infinity, 1 over infinity is 0. So the capacitor will become short circuit. That means. After we know how to convert RLC components from time to phasor domain, we can transform a time domain circuit into phasor and frequency domain, and then we can solve it. Okay, we can apply KCL, KVL, and other theorems. So all the theorems and all the laws that we studied in the previous chapters will apply for the AC circuit. That means, let's say I have this example, refer to this example again. This is 5 cosine of 10t, and let's find the current I. Very easy. This is AC circuit, so I change them to phasor. This remains 4. This one is the inductor, L 0.2 Henry, so I change it to ZL. What is ZL? ZL is j omega L, J10 times 0.2 J2, and the source voltage 5 at an angle of 0 degree. So what is the current? The current is the source voltage 5 at an angle of 0 degree. This is phasor representation over Z. Z is 4 plus J2, the resistance, and the inductor impedance. So the overall impedance is 4 plus J2, and we change it to polar. And you know how to change to polar by using the square root of 4 square plus 2 square, 16 plus 4 over at an angle of tan inverse of 2 over 4. And remember, for division and multiplication, polar form is better to use for division and multiplication, and for addition and subtraction, rectangular form is better representation, because when we do addition and subtraction, we can add the real parts together and the imaginary parts together. And what about for division? We divide the magnitude and the phase. The overall phase will be the phase of the numerator minus the phase of the denominator. So this is the phase 0 minus 26.565 degree. So, and then if we will find the current, what is the voltage across the inductor? The impedance times the current. So what's the impedance? J2 times the current is this one. Of course, what is J means add 90 degree, and it will become 63.45. This is a phasor form, and now we change it to time. We just say cosine of 2.236 cosine of omega t plus the phase. What is omega? Omega is already 10. Easy. So by this way, we can change from the phasor form to time domain, and also from time to phasor form. And this is a practice problem that you should solve it during the class exercise time. Both KVL and KCL hold true in the phasor domain or in the frequency domain. The variables to be handled are phasors, and keep in mind the phasors are complex numbers. And it's not easy when we deal with complex number. Of course, the mathematics, the addition, subtraction, and this, if I have a more complicated circuit, then you can easily make mistakes. Actually, errors can happen unless we do the calculation carefully. The following principles used for DC circuit analysis also apply for AC circuit. Voltage division, current division, circuit reduction, impedance, equivalent impedance, Y delta transformation, superposition principle, Thevenin's theorem, Norton's theorem, maximum power transfer. All these laws and theorems, they apply for AC circuits. Those which we used for DC circuits, they will apply to AC circuits. The only thing here, to simplify the analysis, we need to keep in mind that we use phasor representation. Let's have this example. This example, let's determine the input impedance at omega 10 radians per second. Okay, 10 radian per second. So here you see this inductor is in series with the resistor, and then it will be these two. These two together will be in parallel with the capacitor, and everything will be in series with this. But first we need to change them to phasor form. So 2 NRE J omega L. J omega L means omega is 10. So it will be 2 J20. J20 will be the impedance of this one. And this 1 over J omega C. 1 over J omega C is 1 over J and omega is 10. And this is 4 milli. Remember, it's 4 milli. It will be 1 over J 0.04. If we say this is, for example, Z3, Z3 means this one in series with this one. And if you say this is Z2, so the overall impedance will be Z2 in parallel with Z3 plus Z1. Z1 is the series combination of the 20 ohm and 2 millifarad here. So now it will be a matter of calculation with complex numbers, okay? So Z3 is 50 plus J20 in parallel with the capacitor impedance 1 over J 0.04 plus this 2 is the series combination of these two is 20 plus 1 over J 0.02. What is 1 over J 0.02? Is the capacitor impedance. The capacitor impedance. So then we use the parallel rule. For the parallel is Z, the equivalent is Z2 times Z3 over Z2 plus Z3. And then we add with the series combination. The series combination, when this one 1 over J 0.02 will become minus J50. So this impedance is 20 minus J50. And then I have the parallel combination. And remember, for the division, it's better to change it to polar. First, I multiply these two, and then I get this, and this changes this to polar. And so that the division becomes easier, if you like. Or you can do it directly by rationalization and then do the calculation. After that, we find finally this one. Okay, so the impedance is 32.38 at an angle of 32.38 minus J73.6. So this is the real part is 32.38 and the imaginary minus 73.76. Okay, here is you have an exercise which you will do it in the class exercise session. So again, I have a resistor, inductor, and resistor, capacitor here, and you do series parallel combination, and the answer is given, and you need to do this calculation. Here also, here is another problem. Try to find the voltage, the output voltage across the inductor. So again, you have to use those laws. You can use voltage division, you can use KCL, you can use KVL, but what you need to do, change this to phasor form, and this the capacitor to phasor form, the inductor to phasor form, and apply any of the laws that you studied to find the output voltage as a function of time, which will be given by this. First, you solve it using frequency domain or phasor representation, and then you change it to time domain. That's all about sinusoids and introduction about AC circuits. We studied about phasor representation or frequency domain representation, how to change the circuit elements such as inductors, capacitors to phasor form, how we can solve the AC circuit using the phasor representation, and how we can be able to change from time domain to phasor domain or from phasor domain to time domain. And in the next chapter, we will have more examples to apply the theorems like the superposition theorem and the other theorems that we studied, maximum power transfer and maximum power transfer theorem, the Thevenin theorem, the Norton theorem, and all the others, and the nodal analysis, the mesh analysis for more complex circuits, a little advanced circuits. Thank you for listening to this lecture.